Last week I ended up talking through some of the dynamic analysis tools that were available, and we went through a large number of the monitoring ones, the ones that collect, say, system changes and all that type of information, so that you know, say, what the changes were made on a system during and after a piece of malware was run compared to what it was like originally. This lecture I'm actually going to take some time to discuss, to actually pull apart the attack that we looked at using a debugger. So I went back to the vanilla version of Windows, so I'm reasonably certain that I do not have malware on this VM. I also have it disconnected from the internet, as you can see, just in case. But what I'm going to do now is I'm going to get a copy of that file that we were looking at off of the shared, off of the file share. So it was this invitation. It's right here, and I give it a moment to refresh. There it goes. So I'm going to pull this over here. What you can also see is that we're working from the same image that we had. What I'm going to end up probably doing for this particular lecture is I'm going to end up probably refreshing the VM a couple of times while we're doing analysis as we learn stuff from this malware sample. So before, what I ended up doing was, I loaded up Acrobat Reader. It does this thing, so I'm going to just click no, because I don't want it to prompt me. So I loaded up Acrobat Reader, and then I went in here to open the PDF. What I'm actually going to do this time is I'm going to, well, this is a shortcut, so first what I'm going to do is I'm going to look at where Acrobat Reader is installed. So with any shortcut that's on your system, and this is typically how, say, stuff's organized in Start menu or whatever, so every single one of these programs is a shortcut. It actually points to another location on the system, so I can get that by choosing properties from any one of these shortcuts. That's useful to me because when I want to load up this debugger, which I'm going to use Immunity Debugger, you'll see a decent amount of tutorials and documentation on the internet that talks about using it. So I'm just going to go ahead and use it for the purpose of this example. I did talk last session about a number of different debuggers that are available out there. But basically, I have that open so that when I am going to debug the program, or I should say, when I want to load this up in a debugger, the goal for me with this exercise is that I want to see what's going on when it starts executing the exploit code in this PDF. But the PDF itself isn't a program, so when I open up the debugger and I want to debug the PDF, I actually want to debug the program that's running the PDF. And so that's why I have this open, is so I can find out where the PDF is. So it's in this case, it's in C:program files, Adobe Reader, so I can look through all this stuff, Reader, Acroread32. So Reader, Acroread32.exe. And so now I have the Acrobat Reader loaded up in my debugger. The important thing to keep in mind here is that what happens is it sets up memory, so it does all of the setup stages that Windows would do when Windows normally loads a program into memory, but it stops right before it would start executing the first instruction from the program. So, and you can see that right here. So it loads it up, and it does all the Microsoft Windows OS setup code, which means that for instance, well, I'll go into these in a second, which basically means that it loads all the modules and everything like that in a memory, and then it sets the initial, or I should say the instruction pointer to the first instruction that's listed as the module's entry point. So one of the nice things about this tool is that there's actually a large number of different views that you can use to keep track of the work that you're doing while you're analyzing. One of these is the memory map. So this allows me to see what all the memory locations are mapped to by this program. So it allows me to see in this column what the permissions are supposed to be on those various memory locations. It gives me a description to tell me what the contents are. So for instance, this one, which you can't read very well because of the font. I do not know if I can actually modify that appearance. Can I increase fonts? Let me see. That doesn't look like it's doing much. Try this. No. Here we go. So I can like increase the font size if I want to. So maybe use something like this, and then a bigger font size. There we go. And maybe that's a little bit more readable to all of you. So see, it's got the contents right here. So stack of main thread. So a lot of you are probably aware, when you load a program into memory, the operating system allocates some memory to be used for the stack of that program, or the the local variable heap, that type of stuff. And so that's set up here. In addition to that, here is memory. So I'll show you. It tells you, whoops. It tells you who the owner is. It gives, for instance, list of memory mappings and module name for the owner. So for instance, these are like Microsoft Visual C runtime library, ADV API 32, which is a library, RPC RT4, which is another library, GDI 32, which is another library. So each one of these libraries have their own dedicated section in memory, so that when this program is executing, it can actually directly address data or code that exists in any of those libraries. So and this is the the key component or key mechanism that's used in Windows to handle shared library code, that type of thing. So what happens is this GDI 32, for instance, that's mapped to this address in memory, so this program can use it. And if some other program also happens to be using that same shared library, that may be mapped to the same location or a different location in that program's memory. The important things for us, though, is that Acrobat Reader is loaded up right here, and that's where it's located in memory. So there's actually each one of these buttons here is basically a shortcut to one of these views. I'll show you. There's a log window, which allows you to see some log messages that are generated by Immunity Debugger. So when Immunity Debugger is running, it may, especially if you happen to be using some extra more advanced features to it, it may actually have some code analysis that's done and stuff like that that might log results here. It's actually a pretty extensible debugger, so you can write like little modules for it and stuff like that. Or you can get some from other people. This one has the executable modules. So when I was going through the memory map, you'll remember that I showed you a way to see all the different memory locations that are mapped to within different modules, and also just with basically available for the program to use memory and use resources during execution. This listing is a list of all the modules or libraries and EXEs that are loaded to support this program. So this is the main one here, the one that we're debugging. And then that particular module, the Acrobat module, loaded all these other, what Windows calls modules, what basically are executable libraries into memory as well. So this is almost kind of a shorter list of what you saw, where it's really focused on trying to present to you all the different libraries this program relies upon. This one, so memory, is basically, for all intents and purposes, a one level deeper view of that. It shows you not just every single one of the modules that's loaded, it shows you the subcomponents within those modules, or the sections. So if you recall when we were talking through how Microsoft program or library is divided, it's divided into a series of sections. And each one of those sections contain certain types of data. So for instance, this one is readable and executable. It contains code data. This one is readable and writable. It contains volatile data. This one is readable but not writable. It contains resources, so it contains some static data probably. And then this one is readable but not writable and contains some relocations, which is another kind of nuance of the Windows OS that needs a section to keep track of it. The other thing, let me see, is you have separate access and initial access. So this allows you to keep track of what's the current access restrictions versus what were the access restrictions initially when the memory was first requested from the operating system. And this presents a really useful view into things, where a lot of these were originally mapped as read, write, execute. And then after data was loaded into each one of these, the permissions or privileges on those memory sections were actually restricted after the fact. And this becomes pretty common because when you load a DLL into memory, you have no idea what part of the DLL is actually code versus data until you actually analyze the DLL. So upon analysis, then the system goes and changes the permissions of the subsections to something that's a lot more cautious. So, all right. So at this point, the program that's paused and loaded in memory. So let me see. It hasn't even loaded the window yet. So the window that normally when I double click on Acrobat Reader, it pops up the window and everything. The popping up of the window and all that stuff is actually a sequence of instructions that's run to get us to that point. So another thing we can look at is we can look at the threads. So multiple Windows programs can have multiple threads of execution, which is basically processor states that it schedules between, all living within the same memory space. And so you can actually inspect each one of those. So if I have 5 threads running in a program, I can actually inspect them each independently of one another. This one is supposed to show the windows. So Microsoft Windows manages program windows, so the Windows objects that you see, manages them as top-level kind of operating system data structures. And it keeps an inventory of all of them in memory, so you can actually keep track of the different windows. This particular feature is very useful if you do run into a program that happens to open a window that's off screen, or open a window that's minimized, or open a window that's hidden or invisible for some reason. This will actually allow you to see it and mess with it. Let's see. So this shows the process handles. I'm not going to go through all of these things. This one shows the CPU. So when you're dealing with debugging a program, this is actually one of the, I'm going to shrink this down a little bit so it can actually, I'm going to expand this window. Should shrink that down, should expand the window so that you can see more of it. When you're dealing with debugging program execution or monitoring program execution, this is the primary window, primary view that you'll be using, which is the CPU view. And what this ends up doing is showing you, this is actually very similar to the information that we were retrieving from GDB when I was running that program from the command line in GDB, is that you have the processor right here. So this is the next instruction that's going to run is highlighted with this kind of reverse black on white. The instructions that follow it in memory are down here. You have the current processor state, so all the current status of the registers and everything, including the instruction pointer. So this will always map to that. You also have the data that's currently on the stack, so the program stack. One of the nice features, right? Actually, there's multiple nice features. One of the nice features of the Windows debuggers, especially this one, that can be very helpful for allowing you to navigate the program, is that when it's showing you the data here on the stack, so this is the data that's on the program stack, it, number one, includes the numerical representation, and this is actually in that, this is a number converted, so this byte 67 right here actually corresponds to the G, and then this byte 70 actually corresponds to the P, and then 81 actually corresponds to this little, I have no idea what character that is, and then 7C corresponds to the horizontal bar or pipe character. But what it'll do is it'll automatically identify, for instance, 4-byte sequences, or basically whatever the size of your CPU address space is. It'll automatically recognize when that correlates to something that is a registered memory section. So for instance, in this case, it saw that 7C817067 was on the stack. It looked up and found out that that actually lives, like, I think somewhere over here. Let's see, 7C817067. 7C81, yeah. Yeah. So that actually lives like somewhere here in the code section of the kernel 32 module. So because it recognized that from the other lookup table, it automatically gives you little hints as to what might be going on here. This isn't always a literal, or I should say, this isn't always a factual translation of what the meaning of that data is. It's usually just a hint to whoever happens to be debugging it as to what it might mean. So really what's on the stack is these bytes, and the debugger is attempting to do a lookup for you to provide you with what might be a hint as to what it might mean. So just when you are debugging something, that's something to keep in mind as a possible, some of the information can be misleading, and it's important to know what's going into it. The other thing that's nice is because it has that information. If you remember when we were looking at the DLL file, or we're looking at the exe file. The exe file had information in it that told you what DLLs it wants to use and then what functions it wants to use from each one of those DLLs. So this tool also will attempt to look for those things like this, and it'll tell you what function is attempting to be called by that code. So in this case, Acrobat Reader, for whatever reason, has code down here to call the following Windows function from this library. The other nice thing too is that when you do have something like that, I'm gonna go up here and just, so the other thing too that's nice is that when you do have code like that, when you do get to the point of I should say when the instruction pointer is sitting on this line, if this function takes any arguments, so if it has any arguments, the software is actually able to go, or I should say the debugger is actually able to go and give you some hints as to what values are being passed to those arguments at that time. And that's a piece of information that a lot of times you don't have when you're doing static analysis of the disassembly or static analysis of even the decompiled source code if you ran it through a decompiler. So having...
How can I say whether it is a DLL or not? Is something peculiar to that?
What's that?
And how can I identify whether it is whether it is a DLL or not?
So in Windows, generally speaking, there isn't really much of a difference between something being a DLL or an EXE. If it is listed over here with an owner, or actually let me go up here to the executables section. So, oops. Generally speaking, the first one up here, the top one up here, the one that your execution's starting in, that one is usually an EXE, but it could be a DLL. Well, there isn't really a huge amount of difference between whether something's an EXE or a DLL. As you can see here, it tells you where the path is, and you can use that to try and ascertain that. But otherwise, I mean, I'll say that an EXE file in Windows, you can actually load that into memory using the same function calls that you would use to load a DLL into memory. And you can interact with it as if it were a DLL. And there are actually some EXEs that are built so that they have that sort of dual purpose to them. And really what it is that you have an EXE that exports a number of functions. So it presents a number of functions in its export table that then different other programs can map into their memory if they want to. So that said, what I'm going to do now is I'm going to run this. And so what it basically has is it has a number, these red buttons here are basically the program control buttons, and they help you, they enable you to basically control program execution. So you can run it, you can pause it at any time. It'll be kind of like luck of the draw as to where the program lands. But for instance, like I can click this, and now what it's doing is it's running through execution of of Acrobat Reader. So it's actually loading up Acrobat Reader, but it's also doing a whole bunch of other actions as well. Immunity Debugger actually has some, I guess, a tracing mechanism or something set in place so that when certain actions occur, it pauses execution so it can make a record of that. That's why, number one, Acrobat Reader took forever to load. Number two, you saw all of this, all the activity got recorded to the screen and everything. So like this got updated. This is the modules list. So a whole bunch more modules just got loaded in. And if you remember, when we were talking through some of the Acrobat Reader exploits that existed, there's actually a large number of plugins that exist for Acrobat Reader that it's going to load after Acrobat Reader actually gets to that part of the code. So there's the DLLs that got loaded because hard-coded into the EXE was a list of EXEs that this, or a list of DLLs that AcroRead32 EXE relies upon. So those got automatically loaded by the operating system. Then when Acrobat 32 ran, it has a separate system that inventories all the plugins that it has. So for instance, the Adobe Updater plugin is there, and a whole bunch of other things as well, like the cool type. If you remember, we were looking at one of the exploits had to do with cool type. So it has all these different plugins, and you can see the plugins folder here. How it discovers plugins in the folder, I'm not sure. I'm not entirely certain, but as you can see, there's a whole bunch of different plugins that provide extended functionality to Acrobat Reader. Additionally, there's some other libraries that got loaded into Windows, and what this is showing me here is that while I was running the program, it made all these changes to the content of this window for me, and the changes are highlighted in red so that I can discern what has changed from the last time I ran it. So if I close this and I go back to modules, oh, it's still going to be there. So it keeps track of that for a certain period of time. I believe maybe if I do this and then I start running, I don't know how it decides how to make them, but basically, yeah, highlight stuff in red. That can generally be helpful to you. So, so there's that. I'm actually going to reopen it just because I want to reset everything. I want to see, you can see some of the stuff's happening in here as well. So if I run it, I can actually see a lot of these changes happening in memory too. And I can go and step through and pause. So you can see what it's doing is it's adding it's mapping new memory sections in here as well. So this is program memory. Now it loaded up, right? So, and you can see the last thing that it did, or the last few things it did. It's like this one. Here's some as well, Adobe Link or Adobe Line or something. I don't know what that is. Adobe Update, it's right here. So there's all that stuff. And now Adobe Acrobat Reader is running like that. If I was to pause it, what happens is I can't really interact with Adobe Acrobat Reader. So for instance, since Adobe Acrobat Reader is responsible for redrawing its window and everything and responding to me trying to reach out to it, I can't actually interact with it until I unpause it, and then I can go and mess with it. So it's definitely a hard pause on the application. So next what I'm going to do is I'm going to open that PDF that we were interested in looking at. Actually, I'll go right here and I'll just kind of show you. This is the CPU execution window. This is generally going to show you various, say, snapshots or whatever of. Usually, it's the last thing that occurred. So if I pause it, then it goes here. If I hit play again, I can pause. Well, okay, it doesn't present itself very well. So I'll just kind of step through this. So basically, I have it paused right now, and you can see down here it actually tells you what the program state is. So if you keep your eyes on it, it's running, it's paused. What all the programs are doing basically, just like an operating system, is when nothing's occurring, the program's running in a loop, basically infinite loop, where it's constantly trying to monitor to see if it's been interacted with. Which is why when I do this and I try and change the focus to it and everything, that stuff ends up happening after I unpause it. It's because that's actually all queued up in a message queue for it. And there's a loop running inside the program for that. Because that would be very taxing on the video hardware to sit here and actually render in real time. They don't choose to do that, but instead this CPU display only shows you the state when you pause the program, and then it keeps whatever was shown when you paused the program last when it runs it again. So I'm going to pause it because it's running right now. What you also have is you have these basically 5 different what I call stepping operations, or stepping and tracing operations. So what you have is this one, which is called, it calls it step into. What that does is if you think of a program as being basically a sequence of instructions. So say we were up here at the top of this window. Then it would walk through each one of these instructions until it got to a call, so function call. When we were analyzing code earlier, one of the things I pointed out was that a function that's implemented in code is basically you trying to write almost a custom instruction, for lack of a better term. The way that this is supposed to read to a person is that you do these basic operations here, and then you enter this function, and then when the function's done, you then step to the next one. So from the readability perspective, or readability point of view, this function call really presents itself, at least at this scope, as just another instruction, but with the with the consideration that it's a custom instruction or a user-defined instruction. And the reason why that insight's important here is that the distinction between these two stepping operations, which, well, unfortunately we're here right now, is that they allow you to move forward one instruction and then pause. So rather than executing like all the instructions until you get to a certain condition, it actually will execute the next instruction. So it allows me to walk one at a time and pause the program after every instruction execution. Both of them work that way, the same. The difference is when it comes to calling functions, this one will actually enter the function as a branch in the code path. So when the instruction pointer is changed to whatever the location of this RTL raise exception function is, it'll actually move my view inside that function, and then I'll follow that function until completion. If instead I use this one, what it does is it ignores branching, and it'll just send that instruction, it'll send that function call out, and then it will wait here until that function call returns before providing presentation of where it's at now. That can be very useful when you're walking through code and you don't necessarily want to do basically a breadth first traversal of all the code, which can be very time consuming sometimes. So as I had mentioned earlier, the reverse highlighted, or the black on white, is representing this value right here. I'm just gonna go and look at some of these things to try and see if there's any presentation. Never mind. What that ends up doing is that ends up showing you where the current cursor is, basically. So what I'm going to do is I'm actually going to I'm going to use the step into, and at the return instruction, those of you familiar with that, at the end of the function you return back to where it was coming from. You can actually see where that's supposed to be on the stack here, and it even gives you a hint right here. So where it's supposed to return is the current position on the stack, and that's what this thing is doing here. This is the stack view right here. And then this one I didn't mention earlier, but this is the data view. So this is the view into the data section, and this may jump around according to data modification or data reading operations. This right here is telling you where the top of the stack is. So just like this one is always the instruction pointer right here, this one's always the stack pointer, which is right here. Sorry, I can't see. So the highlighted line here is always going to map to the register value right up here. So you got two registers here that are mapping the cursor position at two of these windows. So what's going to happen is this is telling me that when I return, it's actually going to branch to this address. So I'm going to go and do the return. And then this one tells me that it's going to branch to whatever this address is. So I'm going to do the return. And now I've got a sequence of instructions right here. And sometimes functions call other functions that are very close to them in memory, and sometimes they call functions that are very far away. And so what you saw right there was an example of one where this call right here had actually called, let's see, B2, so it actually called this function right here. And this function ended up being 1, 2, 3, 4 instructions long. So it's a very tiny function. And then after it returned, then we got passed to this. And so what I can do is I can step through this. And the other nice thing too about the debugger is that when I'm walking through it, it also tells me when it gets to a conditional jump, which is what this is. This is supposed to jump if two things were equal. So if the last comparison ended up being 0, then these two things were the same, and if they're the same, then they're equal. And so if they're equal, then it wants to jump to this location, which is 1187, which is somewhere quite a ways away from my current view. But because the 0 flag, and that's what these are over here, is your processor keeps track of state flags, and these are all listed right here. It actually shows you, I guess, it's highlighting which one of these is actually relevant to the current jump instruction. So one of the other neat things that I can do if I really want to mess with program control flow is I can change that. I can set it to 1 instead, and that automatically switches what the behavior is that's going to happen right here. This feature, being able to edit the processor state at runtime, like while it's paused, is extremely helpful if you're trying to work around some sort of anti-debugger or obfuscation or even just some system version checks. So many times, like, I'll have to deal with that type of stuff when I'm debugging a piece of software. So, but I'm going to set this back to the state that it was when we entered this code, because I don't want to cause Adobe Acrobat Reader to crash right yet. So then I can keep going there, and then this one tells me that jump's not taken, and then I can see that this is going to return me to this address, which is completely different memory block, and it tells me that that is actually a memory block owned by the Acrobat Reader program. So this is actually getting me back into my Acrobat Reader code. So what I ended up doing was I loaded up Acrobat Reader, I ran it, I got it to a state where it's basically waiting for me to do something with it. And then I paused it, and when I paused it, I found out that the code I happened to pause it in was actually deep within one of the Windows libraries. And that's frequently going to be the case for many of you trying to debug a piece of software. It's very rare that when you pause the program, you're going to pause it and it's going to be sitting in the same memory space. The processor is not usually going to be pointing to the same memory space that the program that you want to debug is owned by. And the reason for this is because most of the programs that are running in Windows, malware included, rely heavily on libraries that are available in the Windows operating system, so the DLLs and everything. And it calls into those functions and jumps into those modules as if they were just another extension of the program itself. But you don't really care too much about inspecting those particular pieces of code. You want to go and analyze the program. So what I ended up having to do is after I paused it, I ended up using my tracing, so my stepping operations to walk my way back out of the program. Another one that's very handy for that, that's a shortcut to what I did, is actually this one, which what this does is it'll allow execution to keep walking forward, so it won't pause it until it gets to one of these return instructions. So for instance, there's a return instruction down here. So if I was to do this, what it'll do is it'll run all the code, including everything that's inside of these functions, until it gets to that return instruction that I highlighted. So, and then it won't return actually, so it won't execute that instruction until I manually do a step. And so that gives me the ability to try and find where the end of a function call is. If you end up having these setups, which is most commonly the case, where you have a function calling another function, calling another function, calling another function. If you ever wrote complex software, you know that's what it does. This is a way to back out of that, sequence of, shells within shells of programs. So then I'll step out of it, and now I'm in, say, high level function, and I can, and so it looks to me like, so I just hit this till return. It looks to me like what's going on here is this is probably the main loop of the Acrobat program. I can pause it again. So let's see, and then I can step through here, and then what this does is it goes back up to, or it goes down to 4D4, so down here. So, and then what you can see is here's an example of where it is calling this PeakMessageW function. So it's trying to look to see, is there a message ready? And it's basically running this loop where it constantly does that. So then it jumps back up to 408, or it may jump up there. It didn't that time. It jumps up there for some particular case, and this is an unconditional jump back to 419. So then this is back up here to the top. And so what you can see is this is me retracing all that code that I was looking at, and now I'm right back here to the jump instruction. So this is the main program loop. This is me basically being able to follow all the way out of my program pause back out to the main program loop, so I can identify where Adobe does most of its work. So I'm going to go and play this again. So now the program's running. And what I'm going to do now is I'm going to load that PDF. So where did I put it? I put it on the desktop, didn't I? Yeah. So now what it's going to do is it tried to load that PDF. You can see it's still running in the background. But what it says is this access violation when writing to this memory location. Use Shift F7, F8, or F9 to pass the exception of the program. So this debugger, what it allows you to do, or what it does, is it actually catches an exception that's thrown before it's passed down to the program. So earlier when I had mentioned that most of those exploits, what they try and do is they try and break the program in some particular manner. That typically throws a catchable exception in Windows, but the way most software is compiled for release, you generally don't want to have those exceptions be caught by Windows. So they get caught by a standard exception handler that's built into one of the libraries that's shipped with the program, or shipped with Windows that the program uses. And what those generally do is program crashes may write something to an event log behind the scenes, may pop a dialog box up to you, or may do nothing. So what happens with this debugger when you're running it is it actually identifies when where that code will be called, and it inserts itself into that code so that the debugger gets to basically take over whenever one of those exceptions occurs. So in this case, it got an access violation trying to write to this address in memory. So the first thing that I might want to do is I want to go and look at that memory. So that memory location actually happens to be this one right here. And you can see access violation when writing to that memory. Well, as you can see, that memory is actually set to read only, so it's not supposed to be written to. So something in the program actually wanted to write to that memory for whatever reason. So, I'd want to look and try and figure out why. What's it doing? So number one, one of the other neat features of this is that whenever something that is a memory address, so something that's recognized as a number that has a corresponding memory map in the program, whenever that happens to point to a long sequence of human readable data, it'll actually display that data here, so you don't have to go into the memory map to try and figure out what's in that memory location. So you can see that's presented right here. And then there's another one that's showing, it says, it has the word doc name in it for whatever reason. So additionally, the instruction point, or the instruction pointer, is pointing to this BD2BE4. And that's basically what's right here. So what I might want to do is I might want to go and try and figure out what is mapped to that location. So let me see. So that would be the Acrobat code. The other thing too, I've basically verified that, yeah, that's code within Acrobat instead of code that's existing in one of these other things that was loaded, right? So it's code that's actually in Acrobat. So Acrobat got the program crash. The other thing too is that I may want to load this up and try and see what's at the top of this. I don't have any, easy answers on what this data all means, but I can tell you, just looking at it, it has a number of looks like it has a number of different Windows internal strings and stuff like that. However, one thing that's probably worth keeping in mind is that if I was trying to write to this memory location here, maybe I was also trying to write to the memory location right before it, which would actually be in this memory map, which this thing's actually something that's writable, and it's a stack of the main thread, so it's something that would normally be writable. So, that kind of hints to me that there was some sort of, say, stack smashing or stack munging operation going on. So maybe I'll load this one up and see what's going on inside the stack. So I'm going to, one of the things that's really useful in the debugger as well is that looking at all these different memory locations, you can actually display them using different representations that might be helpful to you. So one of the things that I think is particularly interesting here is there's this long series of A's that's written all the way to the end, and if I display this using hex ASCII, it's a lot more apparent what went on. Is that this is F8, 9, A, B, C, D, E, F. So it looks like whatever was happening actually wrote until the end of stack. So it basically got to a condition where it would get to the end of the stack. So they figured out a way to convince Adobe Acrobat Reader to write this character over and over and over and over again on the stack until it ran out of memory, basically, on the stack. When that happened, then there was an exception that was thrown that was then caught. And so that's where we find ourselves today, is so then what I'll want to do is I want to try and see what happens if I pass that exception down. So if I allow that exception handling code that's built into Acrobat Reader, or that Acrobat Reader is using that's built into the OS, I can't remember which one is used here, I want to see what happens when that code takes over. Because I know that when my debugger takes over, my debugger gives me full control, and so it's not going to do anything. What's very likely here is that the attacker intended for all of this data to get written to memory, and then fire off the, and then cause an exception to occur. So the exception's no accident, it's actually intentional. So then, what I'll do is I'll use, so it says you want to push shift plus those things, which basically allows you to override the built-in exception handling. So I'm going to use the step into, which is this one, which is F7, because I'm interested in knowing what happens when a function is called. And so what just happened is that I passed that exception, or I allowed the program to step to the next instruction. Since it caused an access violation, that instruction that it had just executed can't proceed to the next one. It actually threw an exception via the processor that's basically memory access violation that's now caught by the exception handling code. The exception handling code is supposed to then take over and attempt to resolve whatever the problem is. Attempt to either restore program execution after cleaning something up, or even just exit the program entirely. And so that's why this suddenly jumps to this address from that previous instruction that you were looking at. So what this did is the debugger actually stopped program execution right at the instruction that caused the offense, but it didn't jump to the exception handler. And so what you're seeing now is the exception handler that's built into one of the Windows libraries somewhere. So it says right here, tells you which library it's in and which location it is. So it says NTDLL, which is one of the core libraries for the Windows OS. So then what I'm going to do is I'm going to step into this because I want to figure out what's going on. I know, or I should say, if I'm to assume that creating that exception was intentional, which it sure looks like it was because they wrote that sequence of A's, then I'm to also assume that somewhere within this exception handling code it's going to do something, or it's intended to do something that it shouldn't do. And I want to find that. And so what I'm going to end up doing, and this may be a little tedious, so we'll pause for one moment. I wanted to just point one other thing out, which was that if you look over here, it's showing you the arguments that are being passed to this function call that it's hovering over right now. That's what I was kind of explaining to you earlier about the way that this code's able, or this debugger is able to highlight to you and hint to you some of the program control and program flow details as well. So I want to actually go into this instead of stepping over it. So I'm going to keep walking through and seeing what happens. And so it's stepping through a number of different aspects of the Windows exception handling system. So I'm kind of following through this. What I'm looking for right now is I'm looking for either it trying to do another illegal thing maybe, or I'm trying to keep an eye on the different function calls that it's making. And in particular, I want to look for if it's trying to either jump or call to something that is a dynamic value. So this right here, this JNZ, and it has the DLL name here with an address. If you look over here, this is actually the address that this represents, and so this is actually a relative address. And then this one right here is a, what you call it, absolute address. But these values are static, so they're hard coded into the system. You can also call an address that's stored in a variable and stuff like that. That's the type of thing that we would be looking for. So I'm going to keep going through that. And I've already been through this example once, so I know what I'm looking for, but I'm going to try and do it a little slowly just to kind of show you. So what I'm doing is I'm basically going in, so I'm manually doing the breadth first traversal of the program graph, or the control flow graph, if you want to think of it that way, because I want to see where this happens to take over with some user value. If this were to cause another exception, I would get another warning down here at the bottom, just like I had before, that says some sort of access violation or segmentation fault or something like that. So that's also something else I want to keep my eyes on when I'm stepping through this. So sometimes you may run into a situation like this as well. So you see what's going on is I'm stuck in a loop where this is trying to do some sort of search. What I want to do is I want to allow it to go until I get down here. So what I'm actually going to do is I'm going to set a breakpoint. There's two types of breakpoints. There's a software breakpoint where it overwrites data, so it overwrites code with breakpoint code, and then it will insert the code when you catch the breakpoint. The other one you can do is hardware, which actually tells the processor to set a breakpoint at this location. So that's what I'm going to do, and I hope this works. No, it didn't. So I'm going to have to start this over again. But so for this one, this is one of the difficult things of dealing with exception handling code, is that get this out here again. There it goes. So open Acrobat Reader again. Apologies. This one, and then play it. So basically what I want it to do is I want to set a breakpoint there, and then I want to allow it to continue execution forward. The problem is that there's a couple there's unexpected behavior when I'm trying to create a new exception inside of the exception handler, and I just did that wrong. But it's a good learning moment. I'll go ahead now that this is loaded up, and I'll open that thing from the desktop again, and we'll get back more or less to where we were before, which is I'm paused here at this, and so then I'll go and do this. I vaguely, so this is basically going to continue until I get to that loop again, and what I want to do is I just want to try and resolve that loop. So since I know that loop's coming up, I'm going through this extremely fast, because at some point I'm going to get to what looks like this, where I'm just stuck in a loop. So this is a loop that's attempting to do a comparison between these two. So it's actually doing a comparison between this. Let me go back to this again. Font change 12. Come on. Do this. There. So you all can see it. So what it's doing is it's comparing these two things, EAX and EDX. So for some reason it's comparing those two things. I don't know why. And then down here it tries to compare this with basically EDI and ESI, and it's looking for a situation where ESI is actually less than EDI. I don't know why it's doing that. What I'm going to do is I'm going to try this breakpoint again. I'm going to put a hardware breakpoint here, and then instead of instead of hitting play, what I'm going to end up doing is I'm actually going to try doing a trace and see if that'll catch it. So let me I'm going to rewind. So another thing too is I can rewind like that if I happen to do it. And then I'm just going to play again. I'm going to open this again. Here's that. So I'm stuck in this loop again, right here. And what I want to do is under here, okay, it still has the hardware breakpoint for that, so let me try this one. There we go. So there's multiple different ways to run it. What I did was I tried just playing it. I tried doing a trace, that actually executes each instruction and attempts to log activity. And then finally I did the one that I demonstrated earlier, which was try and step through the program until you get to a return instruction. And that's the one that finally allowed me to have the program execution get caught right here. And so what's happening here actually is it's moving this address, so 0D, whatever this is, it's moving this value into the ECX register. What I'm also going to do is I'm going to remove the hardware breakpoint that I set there so that I don't accidentally catch myself later on. And so then what I'm going to do now is I'm going to step, and what it's doing is it wants to add ECX and ESI together. So ECX is this 0D, a lot of zeros, and then ESI is actually this. So what it wants to do is it wants to add this to that and then store the result inside of ECX. So, and then it's got a result of 164 whatever for some reason. So I'm going to keep going. It's a lot easier to do it like this. And what I'm doing is I'm basically walking through more of the exception handler still. So we haven't gotten back to Adobe's program code yet. So in this one I can actually just run it until the return, because I can see that there's nothing of value until I get to the return. And as you can see, this can get somewhat tedious sometimes. So I'm just going to keep going through until I happen to see something like this actually. So I basically kept stepping through and I was trying to keep an eye on specifically these, and this is one of the reasons why these are highlighted for you in red like that, is that they're all control flow and control management operations. So I basically glanced at each one of them until I saw something like this, which is significantly different from all of the other call and jump instructions you saw up to now, because this one actually allows some sort of arbitrary data that's in a register to tell it where it's going to go to. And one of the interesting things about it is that, let's see, where is this at? Stack pointer is at A8, so it's up here. One of the interesting things about it is that the stack happens to have like a whole bunch of addresses in it that are stack addresses. So this sequence right here, it's code that's inside of whatever module this is, which is the mtdll module, pushed a bunch of data onto the stack, so a bunch of addresses onto the stack that actually came from the system stack. This is cutting the instructions off a little bit, so I'll move it, and I'm actually going to resize this for you too. So see all this stuff here. So if I go to the next instruction, what this does is it moves whatever this data is here into ECX, and that happens to be there. So it happens to be this code right here. So then ECX ends up having some sort of code in Acrobat Reader that it then wants to go and jump to. So it's going to go and call into that. And then this ends up executing a bunch of code within Acrobat Reader. So eventually I end up following program execution around. So I'm in some of the code in Acrobat Reader that's designed to try and handle the exceptions. And then I jumped back into the exception handler code here. Let's see. Eventually I'm going to end up trying to execute some sort of instructions that are on the stack. And that's what I'm trying to get to now. And we knew that if I go to the memory here, so if I keep track of this, the stack of the main threads here, CPU view, let me where this is happening. I'm going to breakpoint, hardware breakpoint, do that, and back to this again. It goes through this a couple of times. looking for again is I'm glancing at these control flow calls here, the red ones, and eventually I want to see this thing trying to execute instructions from the stack. And this one might actually, yeah. So then jumps into the program here again. Might not be able to finish this demonstration today. Let me see if I can jump through different hoops that I want to jump through to get to where I'm going. So eventually so what I'm doing now is I'm just following the different returns, and I'm trying to see where this ends up ending on the stack. So it's executing. Here. Let's see. So let me see. I paused it, so we'll see what's going on here. This is also one of the caveats that you can run into when you're trying to deal with debugging stuff, is that sometimes it doesn't always work out the same way as it did the 5 or 6 times before. Here, what I'm going to do, so, yeah, I'm going to run it, and it actually appears that it terminated. This one, though, yeah, so in this case it doesn't look like it actually successfully loaded the exploit. So anyway, walk through a whole bunch of different techniques. What I'll do is I'll mess with this some more, and then I'll bring in kind of what went wrong here into the next lecture, and we'll talk through it some more. I think there was a large amount of helpful information on at least beginning that whole dynamic analysis, debugging analysis step with this particular example.